Hello, in this video I continue to explore ideas from the last theory-packed episode, but on a more practical level. First we will design a framework to create enemies with extreme game process understanding. Then we will use it to create an example opponent for a third-person fencing game prototype. First result will be an undefeatable murder bot that uses computer's precision and calculation prowess to basically never lose. Then we will spend some time making it a bit dumber for us not to create a boring unbeatable encounter. And then in the end, as a dessert, we will talk about why I grew to think this project as a whole is a failure. Also, I can't help but notice that my Patreon somehow grows despite me being late for now 3 videos in a row, and I'm extremely grateful to these wonderful people. Starting from the most important thing about any project, the big why behind it. What exact problem will be solved with the powerful technology we are about to start building? This technology is about building competent force for a longer usage, an antagonist for survival horror about hiding and evading pursuit, a bot to imitate an absent player for an online game or for an offline mode for said game, an opponent for a strategy game like Stronghold or Heroes series that adapts to any map situation instead of following a predefined scenario. In other words, enemies that will face player many times or for a long time at once, that raises the bar for them, because the longer a human individual plays with a bot, the less excited they get, as they start to notice patterns and ineffective behaviors replicating time after time. Now, a short results rewind from our past theoretical findings. We aim to build a two-layer state machine that manages our enemy behavior. But unlike the HFSM approach, where we recursively extend our behavior designs by adding more refinement documented in the next layer that is the same base class, this time we use different abstractions. We fuel our top layer machine with a separate thinking center to make decisions, and states for the state machine are called behaviors. Behavior describes a set of lingering actions, for example, follow a trajectory path, stop and block a hit, or make some aggressive moves towards the player. But behaviors inside are also state machines. They are switching between several states called actions. Action describes a single quantifiable variable of a behavior, in other words, one animation. And the killer feature of this whole structure is that actions are piloted by behaviors with an input package. Although this input package currently holds a single vector field to direct our action, it is the practice that glues together our mechanism, because what we effectively achieve with this is a separation between an animation and physical simulation that is an action, and meta-information that gives direction and enables reusage. For example, the run action moves enemy forward while playing animation, but where forward is at any given moment is actually an information run takes from the last input package. A result of this separation is an ability to reuse actions when we build behaviors. For example, run action is used in wander behavior to run along some 3D path. It is used in pursuit behavior to run towards the player, in avoid behavior to run from the player, and in the attack blocking behavior to turn towards the player for a second before we put up a shield. Multiplication complexity in design, while having additive complexity in implementation. Now, what our components do in order? First one, beliefs. Actually a glorified syntactic sugar process library, but it plays a big role in making our code human readable. It's a long script that contains a bunch of functions for mundane tasks such as different direction, distances, internal constant, and statuses information. I defined it because this functional is reusable, but we use it everywhere, in actions, in behaviors, in decision making, etc. So we can't have unique per abstraction syntactic sugar. Then, brain, the decision center. Its job is to generate a single string return parameter, the name of the most intended behavior for the current moment. Internally, brain uses two pools of intentions, reactive and proactive. These are two similar classes. They have a corresponding behavior they trigger, and they have one method that utilizes beliefs and calculates the value associated with the intention. However, there is a fundamental difference. Reactions are binary, but proactions have their intention presented as a float number between 0 and 1. The choice is done as follows. First, we ask all reactions if they are triggered. If any, we return the first triggered reaction, because reactive behaviors always are more important than proactive ones. Some defense measures or some actions that will have a guaranteed success, for example a melee strike which is guaranteed to connect no matter the player's inputs. However, not always we have a triggered reaction on hands. In this case, proactive intentions are being calculated. This is essentially a one-run maximum search algorithm. Don't pay attention to competence cost for now. Internally, each reaction has a redefined method called isTriggered that returns a Boolean value. As our reactions are discrete in nature, their trigger logic is also discrete. However, proactive intentions are much more interesting to engineer. Their redefined method is recalculate, and in here we must update an intention parameter. Proactive intentions can use utility theory, and for it we have a nice and comfortable Godot tool, an export field of type curve. Now we can create different curves and use them with our code. For example, casual attack proaction, which is to attack the player without a guaranteed success, has two components. First is a comfortable distance. We don't want to attack the player outside of our attacking radius, and we don't want to attack them if they are too close. Second input is impatience curve, which make the enemy's attacking priority bigger if no attacks were invoked recently. Also, speaking about curves, here in beliefs you can find a node called aggression. Aggression is a fabricated parameter that is calculated with curve sampling and also is a part of some other formulas. And why is it a node? Well, it's a nice little class I called feeling. It describes a belief that is universal and can be used by many parts of our program, but needs calculations. To skip calculating it every time a request call happens, we calculate and store it once in a while and return it as stored value. Also, as you can see in the brain algo, we call underscored methods like this instead of redefined one. This is a proxy to mask some universal code for all reactions and proactions. For example, we have here a disabled checkbox. This is a def layer functional to help us analyze behaviors. For example, I can disable navigation tasks to look how does my enemy behave in less noisy way. That's it for brain. Next are behaviors. To understand behaviors, we need to first look at our enemy's main life cycle. So, we have some behavior that we are in. On the start, it's an idle one. Then each physics frame we ask if our behavior is willing to give its priority away. If so, we ask our brain what is the most intended action for the moment. Then here's a little proxy. Essentially, we have a two-tier of behavior being willing to change. It can accept changes, for example, idle state is always willing to change, or it can be forced to change, like you have a single attack line and when animation is done, the behavior is also done, we need to change it, and this two-tier willingness is getting in our way because often brain gives you exact same answer as in the last frame. Example. Wander behavior. It is proactive and it moves enemy to replicate some trajectory. Being practically a dynamic idle state, wander state is always open to reconsiderations. But we often get a signal that wandering is still the most intended thing to do. In this case, we continue to follow our path. On the other hand, paths are finite, and if we just finish to follow one, not only we are willing to give priority, we are forced to do it. In this case, if brain decides that wandering is the most intended thing to do, we execute the change from wandering state to the wandering state, triggering onExit and onEnter methods and choosing a random trajectory to follow again. When our transition routine is done, we ask our current behavior to update the enemy. Behaviors update routine consists of updating our resources, then transitioning between actions inside itself, then creating an input for the current action and asking action to do the quotes down to earth updates like move and slice, etc. Behavior's internal transition logic is similar to the layer above. We check if we are locked in some animation, then we see if we have some forced actions to perform, for example stagger or death, when we finally ask what behavior wants to do. This is a function to redefine by behavior's order. Formulate input is also subject to override, and default one returns a functionally empty object to not return null. An update has a default implementation of calling the current actions update, which can be redefined but is rarely needed. As you can see, there are several instruments to customize behavior's lifecycle, so I created a small template for a new behavior creation, and used methods can be deleted as they all have base implementations. Actions. An action represents one animation. It is similar to our original controller's move class, a bunch of export fields, update, onEnter, onExit methods, and a number of methods to work with time measurement, and a bunch of getters tied to a backend animation framework. These things we already have seen, as well as the rest of node's content. Here we have several bone attachments to store our hurtbox and weapon, and to store visuals and animation player, of course. Now, I want to demonstrate more on Behaviours design with chosen examples. First one is our attack and move, a melee strike. Our initial action is an attack and one, our top layer transition logic is mirroring the player's melee. We force transition after the complete animation end, but we start to be open earlier when the quotes important part ended. Here we have a small function to predict if our attack will hit, and if we understood that we are already missing during the animation, we do a cute little trick of turning around, which completely prevents any whiff punishment by outspacing. These two are just little proxies because I found I mostly input towards the player or away from it. Now wonder. A sort of active idle, but it does an important job for creation of a sense of personality. I looked into Godot's native pathing functional and I didn't really like it, because what the fuck, why a piece of functional should tell me how do I organize my node tree? So I wrote an analog. Here you can see my wonder behavior has a bunch of path 3Ds as a children. They actually are just proxies holding a curve 3D class, but path 3D have the functional to nicely edit said curves in the editor. So on a problem level, we need to learn how to turn this information in the form of Bezier curve into a bunch of directional inputs. To do this, we first tessellate the curve to get a bunch of approximating vectors, then we run along said vectors, writing down our progress. In 2 words, we have an index of current tessellated part we run, and we have a counter for distance we ran. When the distance we ran along is more than current tessellated part, we increment the index of the part, reset distance, and start to move along the next vector. Consequently, our reconsideration readiness is a function of this progress also. We always are ready to give away priority, and we force transition when we ran out of curve to follow. Then there is an input creating geometry problem solution that took some embarrassingly long time to debug. The idea is, for any delta direction, we can break it into tangential and centripetal components by projecting. Then we construct the new translated direction with components of this length, but centripetal component looking at player. Overall, I am satisfied with this approach to an easy curve following. Only one disclaimer: these curves depict wrong information. As my movement algorithm is relative to player, what I really coded is an algorithm for following a number of relative directions to a player. This means that these curves don't depict the trajectory our enemy will draw in the world. They only depict quotes the vibe of movement, and the trajectory itself is dependent on distance to player and players of movements. I chose this approach to simulate a sort of target lock-in of my opponent on the player. If you make some guardian-like patrolling enemy but don't like Godot's approach to navigation, you can take this approach, but you will need to readapt your path following algorithm to be absolute instead of relative to player. Now, blocking action. This is a big topic I want to talk through. This is the first quotes serious modular behavior for us. The plan is start in the running state 2 turns towards the player, such as it was in our blocking sector. Then leave the shield and wait for some time awaiting the hit. Then, if the hit in the front is taken, we play a short locking animation of hit reaction. Simple 3-step algorithm. What can go wrong? Well, turns out they A. have different input generating ways, as turn is inputting a run and block reactions are static. B. They have different reactions on hit, as turn invokes default and staggers, block checks block and angle, block also transitions to reaction, and reaction just blocks. C. They have different priority giving algorithms. Turn doesn't give priority away, block forces transition if no hit was tanked for a certain time, and block reaction forces transition when its animation is ended. D. They have different resource update functions, because under a block we don't restore stamina and we do during the running action, so algorithmically we can get away from a lot of branching or from a distributed system delegating a lot of calls. I want to discuss 3 levels of dealing with such a problem. First one is to face roll the branching. I actually have this solution documented here below under comments. As you can see, here I created a small enumeration to distinguish between my states. Then my choose action function looks like this. We do a single transition with it because the second transition is reactive from block. Inputs are formulated only for the turning phase. Hit reaction is a bit clunky. We check the sector, then we check blocking frames, then if we tank the hit for the first time we transition to block reaction. Our transition openness is also branched. So kinda it, but it is commented to show you another approach. So nature of our problem is to have different processings depending on the situation, and one of better scaling solutions is to compose with something we will delegate the processing and to switch between delegates, although easier said than done. So what concrete Godot measures do we have? We can spam some internal classes. Let's create a small class called block_subBehaviour. It will hold base implementations for input formulation, hit reaction, transition logic and resource updating. Then inside methods on the base behavior we will just call the delegate. For each subbehavior we need to create an heir to block_subBehaviour. Turn behavior formulates input and behaves as a default in all other cases. Block and subbehavior has overridden transition logic and reacts on hit uniquely. All the same is true for block reaction, but they are different. This is the level 2 of preparation work, and level 3 I haven't here prepared, but theoretically you can go ham and create behavior that will be a scene and a world in itself, having fat states, yada yada yada. The main question though is why? Even here, if you will look, our sexy OP solution actually takes much more lines to write than a simple enumerated ifs collection. Well, the why is simply scalability. For this behavior, full-blown OP is probably an overkill and can be used by all those haters to illustrate bad videos. However, behaviors can be much more complex. Here's the flow of pressuring a slow weapon with a faster one from Souls series. As you can see, we have several branches, we have different exit triggers, and we use at least 5 animations. Theoretically, we might want our opponent to execute such move sequences, but I want to assure you that the scope enumerated if statements probably won't cut it. Hence I am showing here this alternative method with internal classes. This is all for analyze. Obviously I have more behaviors, but they are not so interesting to talk about. Most actions also have extremely easy code and are managed by expert fields and backend animations. Beliefs have a lot of work done, but that's mostly small geometry problems. Here is a small demonstration. And here we have a problem. We can defeat this thing. So let's discuss what can we do to actually make this thing honest and interesting. There are 2 general approaches to make a machine stupider. Make it make less decisions and make its decisions worse. For example, there is an effective technique to just skip a thinking frame once in a while, like 1, 5, 10%. And the percentage of the frames we skip is the parameter that we can regulate with difficulty curve. But I don't think this approach will work for us, because we actually don't make that much decisions that matter. Like, the real decision that matters is brain's output when current behavior forces transition on some crucial animation end. And you kinda can't take that, what the character gonna do. Freeze? So for this case I think we better make our decisions worse. Let's think how. First thing I considered is a resource or feeling of competence. The idea is to have some parameter to serve as a sort of stamina for good decisions. Decisions then can cost indent resource and it will slowly regenerate. The thing you see on your screen actually already has that solution in place, just with infinite competence. As you can see, bot is programmed to occasionally casually attack us when we are inside attack radius, and it takes pretty much every opportunity to make this choice. Now, let's make competence regeneration somewhat equal to stamina regeneration. Still attacks us from time to time, but it's much more tame. Obviously, we balance our outputs in a way that the best decisions cost more and neutral decisions cost less or up to zero. Okay, we tamed it a bit, but we still have an infinite difficulty problem because bot is not so aggressive, but it doesn't need much competence to never take a hit. If we attack, it always can block or roll away, and we can't outspace it because with our own hands we installed here a defensive mechanism countering any outspaces. The solution for me seems to make some of those triggers disappear. For example, artificially create a chance that some reactions straight up won't fire, something like this. And now we can actually kill it after some training. Now the juicy part. What educational content can you invent that will be better than somewhat competent individual reflecting on their mistakes? I think that this project is a failure. The code actually is nice, I like it. I am proud of that I managed to build two store-state machine without lower level exploding in complexity in duplication. I like my abstractions choice and I have ideas on how to build even the most complex behaviors I can think of. If I will need a very intelligent foe for my game in the future, I will probably go with this framework. What is a failure is me promising to do it. To myself and to you, then doing it and then creating this video with all possible deadlines broken. There are three interconnected topics I want to discuss, or rather one topic I want to discuss from three different angles. Never ending, imperfect, and too specific. That is the characteristic I would give to the results and work processes around this demo. First part of the problem is I think the enemy I created in the end is too boring to play against. And that is not the function of its intellect, it is the function of its lacking complexity and depth. This is a trap because depth doesn't come from the amount of content, depth comes from the amount of possible behavior transitions. Behaviors are built from actions and our problem can be formulated as it just knows too little tricks, but that's not the best way to put it. The better way to say it is it has too little systems to interact with. We can add 10 more animations here, but it won't cure the problem. We must add 2 more animations 5 times, creating new ways of using them. If you wish, we need to up connectivity in our graph and not necessarily the amount of vertices. This slowly moves us to another angle. I kinda need to do too much to make this endeavor into a worthy demonstration product. Throughout the creation of this enemy, I couldn't help but think, damn, I am creating a game, don't I? And counterintuitively for a game dev channel, this is a big mistake on my part. This is a problem. To create an indie game is a quest. It is a deed to achieve, it takes a long time and it is done with some goal in mind. There are different goals for an indie to choose from, but none of them is a goal to make a video that maybe will get 1,000 views after a week. But that's a cheap way to cry about ambition. The real problem is the trap of scope. To make it good, I need too much to do, but to make it bad is kinda non-existent alternative as it's not bad by any mean, it is just unfinished, which is much worse. A very demonstrating thing to look at is how many to-dos I left untouched while creating this demo. Any of my code actually looks like this, you just don't see it usually. But to count, read and understand them I think is a useful experience to understand my frustration. Weapon parameters of attack. Shield parameters for blocks, so to do this enemy cleanly, I need to invent things I didn't even invent for the controller yet. A lazy shit code that doesn't take vertical level designs into account, so to make this enemy cleanly I need to also create at least a simpler side test arena, and I search in opponent, but here's also a catch. I added about 200 lines into player's controller for proper communication, so creation of such an enemy kinda forces us to change and or create a bunch of other systems, and the number grows like a snowball. What I came to is, when you have an enemy of such intelligence and interactiveness level, your game sort of becomes about it. And here we come to the third angle to look from, and another reason I didn't like how similar this process was to creation of a game. I catched myself being the thing I don't really like and respect in our industry. I created a demo about examples more than about systems. This is an educational game dev channel, and I name my videos and playlists as tutorials, but in my heart I believe that tutorial is an overused and unhealthy genre. Tutorials are about examples, and current situation in the teaching sphere is tutorial oversaturation. I don't think we need so much examples of how to do one concrete thing in one concrete way. So, while using this forsaken term, I tend to create content that I would honestly call lessons. I want my videos to be about systems. I believe that people en masse don't need to know how to solve one of their particular problems. I believe that what people really need is to learn how to think, to invent better solutions themselves, and from this point of view, this demo is not that much about systems, like what new information did I input? Hard boxes and weapons we have already discussed. Animation player and backend animations we have already discussed. The concept of state machine and all its incarnations is sucked dry. Current incarnation is very curious, but like the principal scheme of architecture was ready in the last fully theoretical video, so I have this terrible itching that this video was too much about smaller side techniques. How to use curves to form your feelings, how to construct your belief system, how to milk polymorphism and inheritance to its fullest with inner classes for complex behaviors to work, how to use Path 3D to create an alternative to Godot's path following cringe, and I don't think I add much value to humanity doing this. This is too exampleful, too concrete. Now, what positive things can I see and take with me from this catastrophe? The first positive thing I will take from all this situation is when you create an enemy that will interact with most of the game's systems, you first need those systems in place. Cringe and obvious, you can say. Well, here I am. Tried to face roll it and hit my head into the wall. The second thing I think of is to stop. I seriously don't think I will continue the enemy series further, because as I foolishly promised in the very first episode, each next step must be more epic, and two themes we have left are higher-end functioneer and then the programming of the crowd of enemies director. I currently am not decided, but one thing is obvious. I wouldn't be able to create a high-end functioneer in any reasonable time. Like, what options do we have? A stealth game guard with multiple patrolling strats, communications, signalizations and lockdowns? Well, I basically need to write a full mini stealth game. Some farmer or restaurant manager like in Soto strategies? Well, we need to create one first. Side note is I now went to the other side of the screen and I do understand why Go-op algorithm reviews are so bad. Like, everyone uses two miserable examples about choosing between hunting and gathering, or an example about grabbing a weapon, opening the door and attacking the player. Yeah, those are miserable, but have you tried to build a proper demonstration for an algorithm such strong as Go-op? It will take several hundred hours. Of course people blast their lungs about hunting and gathering instead of doing something so hard. In some universe there is a chance that I will find some 3-pack with a lot of assets and we will create our functioneer in a 2D fashion for sake of easiness of creation and only to create systems and mechanics, while assets creation phase will be skipped. I don't know, maybe, but I also want to spend some time creating smaller episodic videos, maybe a bunch of singles, or maybe start parkour series which is full of systems and not so full of examples, because Because I need to unburn out myself a bit, as I noticed that I grew cold to the idea of working with this concrete 3D project of controller plus proto level plus whatever the current theme is. I am very sorry, and I feel in some sense I am betraying a part of audience, but in the end, to stop a series from progressing is better than to stop the channel next month because I am weak human or something.